What's going on, everybody, and welcome to part 2 of the neural networks from scratch videos. In this video, what we're going to do is just continue building upon what we've got so far. The first order of business, however, I am going to change all these values, and moving forward, I'm going to keep doing this to be exactly the same values that we use in the book. That way, if anybody is following along there, the videos are going to match the book exactly. So the first thing that we're going to do is we're going to change these inputs. These are going to be 1, 2, and 3. And then the weights, and again, these are just totally made up values for now. Later, the neural network will randomly initialize weights, and then what's going to be tweaking those weights is really like back propagation. So for now, though, we're just making them up, but I just want to use the same made up values as from the book. So 0.2, 0.8, and negative 0.5. And the bias used was 2. So running this, we get 2.3. That's what we wanted. So, okay. So now that we've got that, I got a couple of questions about, why is there only one bias? And then some people were asking about weights. So I've just kind of re-explained weights, but why only one bias? So if that's kind of confusing to you, let's take a peek-see at what we've coded so far. So imagine you've got this full neural network. Okay, it's fully connected, all that. And then what we've done is we've selected a single neuron from that network. And in this case, that neuron had 3 inputs to it. Now looking at this, you can already see, okay, we've got 3 connections, but only 1 neuron. So in terms of bias, there's only going to be 1 bias associated with this neuron. But because we've got 3 inputs, that means we have 3 weights. So every input has its own unique weight, but every neuron just has its 1 bias. You don't have a bias per weight. So from here, what's happening is, yes, we've got the exact same inputs that I've coded here, the weights that we've got here, the bias that we've got here, and then basically all this just gets added into this massive formula here of inputs times the weights plus the bias to give us our final output of 2.3. So now what I'd like to do is let's add one more input in this case. So before we do that, though, I want to kind of solidify what exactly are these inputs. So these inputs in theory could be one of 2 things. It could either be truly input as in like values from the input layer of a neural network, which is just going to be a vector of values. So in theory, this could be an example of an input layer. Now, in the example that we showed visually, that is exactly what it was, right? We had this fully connected neural network, and then we kind of singled out that one neuron that was in that first hidden layer. And in that case, it was pulling values from like the first true layer, which would be our input layer of the neural network. So what is that input layer? That input layer is simply whatever values you have that you're tracking. So let's say you've got an example that you're trying to predict failure or not failure for servers or computer equipment, right? And so you've got various sensors like heat sensors and humidity sensors and stuff like that, right? So each value here in these inputs, if this is your input layer, each unique value here could be a value from a separate sensor. Now, later when we add 4 inputs, we're going to kind of simulate it's coming from somewhere in the middle of the neural network. So your inputs to a neuron could either be from the true input layer that are values from something like, say, a sensor, or a group of sensors in this case, or they could be outputs from neurons themselves. So I'll show an example of that when we get there. But for now, let's say we add one more input. So 1, 2, 3, and then a 2.5. So now we've gotten there. So again, we have this same fully connected neural network, but this time what we're going to do is we're going to select a different neuron. So as you can see, actually this time we're going to model one of the output layer neurons. In this case though, the calculation is going to remain totally the same. Now in the future, when we start calculating the activation functions, you'll see that the output layer will have a different one. But for now, the calculation of inputs times the weights plus the bias, that actually stays the same. So the other thing that's different here is this neuron is taking inputs from not maybe sensors or whatever. It's actually taking inputs from one of the hidden layers. But it turns out it outputs the same stuff, right? So in this case, for this neuron with 4 unique inputs, what's going to change? Well, you're just going to have one extra unique weight, but do you have any extra biases? No, we're still only modeling a single neuron. It doesn't matter that 4 neurons were the input to this neuron because the outputs of those 4 neurons become the input of the new neuron. And once that neuron has already generated its output, it's already, if it was like a hidden layer neuron, it's already taken into account the bias. So in this case, again, when we're modeling 4 inputs to a single neuron, we're only going to have a single bias. So let's go ahead and code that. So really all that changes here is, yes, we've got the 2.5. The weights actually, we need one more unique weight, and in this case we used 1.0. 1.0. And then the only change here is quite simple, right? We're just going to copy, paste, and then I'm going to just modify this 3, and then come over here, 3, and then just scrolling out. I think it's pretty easy to follow at this point. Very simple, as Part 1 Harrison would say. And yeah, cool. So let's go ahead and run that, and we get 4.8. Very simple. So now, what happens if instead of modeling, so in this case we were modeling only 1 neuron but with 4 inputs, and then before that 1 neuron with 3 inputs, what if we want to model 3 neurons with 4 inputs? So in the case of 3 neurons with 4 inputs, what we're looking at is going to be something like this. Now in this case, what we're doing is we're showing basically the output layer. As you'll see later on, the output layer will have some differences, but the first part of doing the inputs times the weights plus the bias is going to indeed be identical. All right, so code-wise, what we're going to need here is if it's 4 inputs into 3 neurons, this means the inputs are going to stay the same. We already have 4 inputs defined. But what we're going to need are, since there's 3 neurons, that means there's going to be 3 unique weight sets. And each weight set is going to have 4 values because there's 4 inputs. And then for biases, we're also going to need 3 unique or separate biases. So let's go ahead and code that in. I am going to just copy, paste. We're going to call these weights 1, 2, and 3. And then for bias, we're going to copy, paste, and we're going to have bias 1, 2, 3. Now, for the people who are like absolutely crying right now, we will eventually convert this to a loop, and then eventually we won't even be using raw Python anymore. We're going to use NumPy to kind of go through this and make this way better. But for now, we're keeping it very simple just so nothing is lost on anybody, hopefully. So what we've got here are, weights 1, 2, 3, and what I'm going to do is I am going to, again, use the exact same values from the book. So 0.5, negative 0.91, 0.26, negative 0.5, and then for weights 3, it is negative 0.26, negative 0.27, 0.17, and 0.87, and that is actually not a negative. Cool. For bias 1, it's still a 2. Bias 2 will be a 3. Bias 3 will be 0.5. Hopefully I got that right. Okay, so that's changed. Now, what is going to change here on the output? So when we're just modeling a single neuron, the output is going to be a single value. In this case, though, we're actually modeling 3 neurons. So we're modeling a layer, so to speak. So the layer output is going to look an awful lot like the input. So in this case, the input, again, it could have been maybe the input layer, but it could also be input from other neural, like another layer in the neural network. So the output for this should look an awful lot like this, only rather than having 4 values, it should have 3. So let's make that change. So what we're going to do is basically convert this. This will now be a list. And I'm going to say comma here. And I think we should be able to get away with copy. And what we'll do is come down here, tab, paste. Now, inputs will always be 0, 1, 2, 3, okay? But weights, now, what we're going to need to do is change this to 1, 2, 3, 1, 2, 3, 1, 2, 3, and then again here, 1, 2, 3, and then bias needs to also be 1, 2, whoops, 2, 3. And don't forget your comma here. And yeah, I think that's relatively acceptable. Let's go ahead and run that. And what we see here for the output for this these 3 neurons is 4.8, 1.21, and 2.385. So again, looking at everything, you've got your fully connected neural network. We've selected 3 neurons with 4 inputs each. Those 4 inputs for every neuron will remain the same, but what's different is each neuron is going to have a unique set of weights for each unique input, and each neuron will have its own unique or separate bias. So when modeling for the first neuron, you've got your weight set 1. Your second neuron is going to have your weight set 2, and it's also going to have its own bias. And when modeling for neuron 3, again, its own unique weight set, its own unique bias, and it will also have its own unique output, same with all of the other neurons. And the calculation for that output is just simply going to be those inputs times those weights plus the bias. So because we've got 3 neurons, it's going to be 3 unique outputs. And each of those, again, the calculation is pretty simple. It's just inputs times the weights plus the bias for every single neuron. Okay, that's all the code for now. If you have any problem understanding anything up to this point, please ask your questions below. If you're a little confused about like what weights are, this should start to become a little more obvious. So imagine you want to start changing these output values here. How would you do it? Well, you have 2 options, right? You could start, because the inputs, you can't really change the inputs because the inputs are outputs from like either a previous layer or they're like your actual data from, your actual input data from features like sensor data or something like that. So you really can never change the inputs directly, but you actually can by changing weights and biases. So you can change, because the inputs, what are those? Those are outputs often from other neurons. So how do we tweak those? Well, we do that by tweaking the weights and the bias, right? So that is the struggle of deep learning, is figuring out how best to tune those weights and those biases. But that's how we can start to have an impact on these output values. And when we get to it, that is the whole, crux of deep learning, is the kind of backpropagation, calculating gradient, and like figuring out how do we adjust weights and biases to get the output values that we want for like the vast array of inputs that we might have. So anyway, if you are confused about weights and biases, hopefully now it's starting to at least become clear that, okay, to change, to actually make an impact on these outputs, the way that we would do that is by tweaking these weights and these biases. Now, how we do that is a mystery that we will be solving much later in the series. But for now, my hope is that all of this is very clear Python code. We will be cleaning this up. We're going to convert this. Well, first I'll just show, like, obviously we can loop through this. We can make this into array data first, and then, but also when we do that, we're going to have to talk about arrays versus tensors, which is a surprisingly heated topic sometimes. Matrices, all that. So we have to cover a little bit more about that, and then also some other operations that we're going to be performing. So anyway, that's all for now. Questions, comments, concerns, feel free to leave them below. If you're interested in the book, you can get it at nnfs.io. Eventually the draft will be complete, but the book is, even right now, even though it's in draft form, is basically everything from starting to code your neurons, all the activation functions, to actually training, backpropagation, actually getting the neural network to go through a training loop and actually learn things. Even we've just released the regularization section as well. So if you're watching this on release, that's kind of where we are right now. Pretty far along, certainly much further along than this. So if you're looking to get a jump on the material, that's how you can do it. And again, nnfs.io. Otherwise, I will see you guys in the next video.